All right, in this lecture, we're going to discuss transformations of random vectors. Let's start by defining functions of random variables, or more generally, Borel measurable functions. The Borel measurable sets on a space R to the n, which we denote as script B of R to the n, are generated by the collection of pre-images of intervals under projection, that is, sets of the form Pi sub E inverse of interval minus infinity to x inclusive, where x is a real number and I is a component index from 1 to n. A function g mapping from R to the n to R to the m is called a Borel measurable function if the preimage under G of any Borel set in R to the m, G inverse of Bm, is a Borel set in R to the n, an element of script B of R to the n for any Bm in script B, R to the m. Now a proposition, consider a random variable x mapping from omega to R defined on a probability space omega script f p. Suppose G is a function from R to R such that the pre-image G inverse of the interval minus infinity to x inclusive is a Borel set in R, an element of script B of R for all real x. Then G of x is also a random variable. Let's walk through the proof of this. We can represent G of x by a new map y from omega to R such that y of omega is defined as G composed with x evaluated at omega for all outcomes omega in omega. Now we need to check the condition for y to be a random variable. For any half open set Bx equals minus infinity to x, the pre-image y inverse of Bx is x inverse composed with G inverse of Bx. Since we are given that G inverse of Bx is an element of script B of R, the Borel sets on R, it follows from the definition of a random variable x that x inverse of any Borel set is in script f, that y inverse of Bx is in script f. Thus, y, which is G of x, is a random variable. Let's consider an example, a monotonically increasing function of a random variable. Let G from R to R be a monotonically increasing function. Then, for any real x, the pre-image G inverse of interval from minus infinity to x inclusive, which will be an interval of the form G inverse of minus infinity to G inverse of x, is a Borel set in R. Now consider a random variable x mapping from omega to R defined on omega script f p. Then y defined as G of x is a random variable. Its distribution function fy of y is the probability that G of x is less than or equal to y. Since G is monotonically increasing, this is equivalent to the probability that x is less than or equal to G inverse of y, which is just fx of G inverse of y. G inverse of, here G inverse of y is the standard functional inverse, not the set preimage we were discussing earlier for general Borel sets. However, we can think of G inverse of y as G inverse of the set y. Since G is monotonically increasing, this inverse image, if it exists for y in the range, will contain at most a single element. Let's look at another example. A monotonically decreasing function of a random variable. Consider a positive random variable x mapping from omega to r plus, defined on a probability space omega script fp. Let g be a function from r plus to r plus such that g of x equals e to the power minus theta x for all x in r plus and for some positive theta. Then g is a monotonically decreasing function of x. The inverse function x equals g inverse of y is minus 1 over theta times the natural log of y. This implies that the preimage g inverse of the interval minus infinity y inclusive for y in r plus, and noting g maps to positive values is the closed interval from minus 1 over theta ln y to infinity. This interval is an element of script b of r plus for all y in r plus. Thus g is a measurable function and y equals g of x is a random variable. Now, a proposition regarding the independence of functions of random variables. Let g from r to r and h from r to r be functions such that their preimages of intervals g inverse of the interval from minus infinity to x inclusive and h inverse of interval minus infinity to x are Borel sets for all real x. This means g and h are Borel measurable. Consider two independent random variables x and y defined on the same probability space omega script f p. Then g of x and h of y are also independent random variables. Let's sketch the proof for this. For any real numbers u and v, we can define the pre-images ag of u as g inverse of interval minus infinity u and ah of v as h inverse of interval minus infinity v. Since g and h are Borel measurable functions, ag of u and ah of v are Borel sets in R. Now consider the joint event g of x is less than or equal to u intersected with h of y is less than or equal to v. This is equivalent to the event x is in g inverse of interval minus infinity, u intersected with y is in h inverse of interval minus infinity v. This in turn is x inverse of a g of u intersected with y inverse of a h of v. Since ag of u and ah of v are Borel sets, x inverse of ag of u and y inverse of ah of v are events in script f. Since x and y are given to be independent random variables, it follows that the events x inverse of ag of u and y inverse of ah of v are independent events. The probability of their intersection is the product of their probabilities, which means p of g of x lesser than or equal to u and h of y lesser than or equal to v equals p of g of x lesser than or equal to u times p of h of y lesser than or equal to v. This establishes the independence of gx and hy. Now let's extend this to functions of random vectors. Consider a random vector x mapping from omega to r to the n defined on omega script f p. Let g be a Borel measurable function from r to the n to r to the m. This means that the set AG of y defined as the intersection from j equals 1 to m of x in R to the n such that gj of x is less than or equal to yj is an element of script b of R to the n for all y in R to the m. Then g of x, which maps from omega to R to the m, is a random vector. The joint distribution function fy of y for the random vector y defined as g of x is given by p of x inverse of ag of y for all y in R to the m in R to the. Let's look at an example. The sum of random variables for a random vector x from omega to R to the n defined on a probability space omega script f p, define an addition function, let's just call it plus, from R to the n to R such that plus of x is the sum from I equals 1 to n of xi for any x in R to the n. We can verify that this addition function is a Borel measurable function. Hence, y equals plus x, which is the sum from I equals 1 to n of xi, is a random variable when n equals 2 and x is a continuous random vector with a joint density fx from R square to R plus. We can write the CDF of y, fy of y as p of y lesser than or equal to y, which is p of x1 plus x2 lesser than or equal to y. This is the integral over x1 in R of the integral for x2 less than or equal to y minus x1 fx of x1 x2 dx1 dx2. By applying a change of variable, let t equals x1 plus x2. So x2 equals t x1, and then changing the order of integration, we see that fy of y equals the integral for t less than or equal to y of dt times the integral over x1 in R of dx1 times fx of x1 t minus x1. When y is a continuous random variable, which it often will be if x is, we can find its density fy of y by differentiating fy of y with respect to y. This gives fy of y equals the integral over x in R of fx of x y minus x dx. When x mapping from omega to R squared is an independent random vector, meaning its components x1 and x2 are independent, then its joint density fx of x factors into the product of the marginal densities fx1 of x1 times fx2 of x2 for all x in R squared. Therefore, the density of the sum y equals x1 plus x2, which is fy of y, becomes the integral over x in R of dx times fx1 of x times fx2 of y minus x. This integral is precisely the definition of the convolution of fx1 and fx2 evaluated at y. We denote this as fx1 star fx2 of y, where star is the convolution operator. Now, for a more general theorem for functions of random vectors, often used for finding the density of transformed continuous random vectors, for a continuous random vector x from omega to R to the m defined on omega script f p with density fx from R to the m to R plus, let G be an injective 1-to-1 and smooth Borel measurable function from R to the m to R to the m such that y equals g of x is also a continuous random vector. Then the density of the random vector y, fy of y, is given by fx of x divided by the determinant of j of y. Here, x is g inverse of y, which is unique since g is injective, and j of y is the Jacobian matrix of the transformation g evaluated at x or expressed in terms of y. The Jacobian matrix has entries ji of y equal to the partial derivative of yj with respect to xi for ij in 1 to m. Let's look at the proof of this transformation theorem. For an injective map, G from R to the M to R to the M, for any Y in the range of G, G of R to the M, the pre-image G inverse of Y consists of a single point, X. Further, since G is smooth, we can relate infinitesimal volumes. Di is approximately j of y times x plus higher order terms O of determinant dx. Thus, the determinant volume element is approximately determinant j of y times determinant dx plus O of determinant dx. Let's call this as equation 1. Now, defining an infinitesimal hyperrectangle dB of y as the set of w in R to the m, such that yj is less than or equal to wj, which is less than or equal to yj plus dij. We observe that for any continuous random vector y, the probability p composed with y inverse of dB of y is fy of y times determinant di. This must be equal to p composed with x inverse of dB of x, the corresponding infinitesimal region for x, which is fx of x times determinant dx. Let's call this as equation 2. We get the final result by combining equation 1 and equation 2. Let's revisit the sum of random variables example using this theorem. Let x be a random vector from omega to r squared and define y1 equals x1 plus x2. We want to compute fy1 of y1. To use the theorem, we need a transformation from R2 to R2. So let's define a new random vector y from omega to r squared as y equals x1 plus x2 comma x2. Let y1 equals x1 plus x2 and y2 equals x2. The inverse transformation is x1 equals y1, y2, and x2 equals y2. The Jacobian matrix of the transformation from x to y, y1 equals x1 plus x2, y2 equals x2 has partial derivatives dy1 by dx1 equals 1, dy1 by dx2 equals 1, dy2 by dx1 equals 0, dy2 by dx2 equals 1. So the determinant value of j of y is 1. This implies that the joint density fy of y, which is fy1, y2 of y1, y2, equals fx of x, which is fx1, x2 of x1, x2, where x1 equals y1, y2, and x2 equals y2. So fy1, y2 of y1, y2 equals fx1, x2, y1, y2, y2. Thus, we can compute the marginal density of y1 by integrating out y2. Fy1 of y1 equals the integral from minus infinity to infinity of fx of x with the conditions x2 equals y2 and x1 plus x2 equals y1 dy2. This becomes the integral from minus infinity to infinity of fx of y1 minus y2 dy2. If x is an independent random vector, then fx of x1 x2 equals fx1 of x1 times fx2 of x2. So fy1 of y1 becomes the integral from minus infinity to infinity of fx1 of y1 minus e2 times fx2 of y2 di2. This is once again the convolution of fx1 and fx2 evaluated at y1. This concludes our discussion on the transformation of random vectors.